In this video, I'm going to talk about the technique of trig substitution for solving integrals. We've talked about how to solve a number of different types of integrals so far, but we haven't talked about how to solve integrals of these various types. Really, this could be any constant squared, an a squared in this case, but what happens if I have the square root of something minus x squared? I can't use a u substitution because there's no, if u is equal to this thing, there's no additional x anywhere. Turns out I also can't do integration by parts because if I added in a clever one, that's the only part that I could add in, it doesn't work either. What other techniques? Those are really, and there's nothing. So what are we going to do? We're going to do some trig substitutions, and let's just start off the bat with an example. So I'm going to use some clever background knowledge, and maybe it's not that clever. I'll bust out this table. Where's my table? I need a little table. Bust out my table of some trig identities that you know from way back in the day. I expect everyone to know that sine squared plus cosine squared equals 1. And that means that 1 minus sine squared is equal to cosine squared. And that's the thing that I'm going to take advantage of in this particular integral. How cool would it be if instead of an x squared here, I had a sine squared theta? Because then the square root of that would just be the square root of this, which would be cosine, which is pretty nice. So that's exactly what we're going to do. And it turns out when we do that, it adds a little extra complexity. It's sort of like a backwards u substitution. With u substitutions, usually I set u equal to some big thing. In this case, I'm setting x equal to a function of theta. So I'm going to let x equal sine of theta. What does that mean? That means that the derivative, that's what x is. What's dx going to be? That means that dx is going to be equal to the derivative of sine, which is the cosine of theta, d theta. And we can convert this old messy integral into something that's a little bit nicer. In this case, this nicer integral is the integral of the square root of 1 minus, I'm changing x into sine of theta squared, and I change the dx into this whole thing, cosine theta d theta. And why did I do this? I did this because now I can make use of the trig substitution that 1 minus sine squared is cosine squared. So this becomes the integral of 1 minus sine squared is cosine squared theta times cosine of theta d theta. And the square root of a square is just cosine, so I get the integral of cosine theta times cosine theta d theta, which is the integral of cosine squared theta d theta. If you remember from our previous section, this is one of the classic ones that is really hard to do by hand, and so it's one of the few trig integrals that it's sort of nice to memorize. So I had to look up to double check that the integral of cosine squared of theta d theta is equal to theta over 2 plus 1/2 of the sine of theta times the cosine of theta plus c. So notice we've gotten a solution, that we set this up, we did the integral, and we were able to integrate with this substitution using a table as well. But this answer is not given in our original variable x. So our next step, our final step, is that we have to convert back to x's. And in order to do that, I always have to draw a figure. So let's remind ourselves, what is the relationship between x and theta? We have that the sine of theta, which is equal to the opposite over the hypotenuse, this is a trig identity, is equal to x, which is the same thing as x over 1. So if I draw a right triangle, I know that the sine of theta is equal to the opposite over the hypotenuse, which is x over 1. That means that this remaining side by Pythagorean theorem is going to be 1 squared minus x squared square rooted. Why is that helpful? Now when I go back and have to convert each of these pieces, it's easier to see what cosine of theta is going to be. Sine of theta is x over 1. Cosine of theta is equal to adjacent over hypotenuse, which in this case, adjacent over hypotenuse is the square root of 1 minus x squared. So now we have our final answer. Our final answer is this integral. Oh, maybe I should say, well, what's theta? If x is equal to sine theta, that means that theta is equal to the inverse sine of x. We have to be a little careful about domain, right? Because these inverse trig functions have really limited domains. But notice that this original function also has a limited domain. It's only defined between x equals -1 and 1. Otherwise, you get negative radicals. So it turns out our domain works out okay. I'm not going to be a stickler for domains, but I wanted to just mention it. So converting back, it means that theta is the inverse sine, or the arc sine of x. And then we get plus 1/2 of, what's the sine of theta? The sine of theta is x. And what's the cosine of theta? I used my triangle over here, and I found out that the cosine of theta was the square root of 1 minus x squared plus c. And that's our final answer, and it's messy. But it's a cool technique to be able to convert trig, to be able to integrate, and then to move back again. We're going to do another example, and this example is going to be a little bit messier. In our previous example, we had a coefficient of 1, and this time we're going to have a coefficient of 9. And we're going to try to use the same thought process. What sort of trig identity can I use so that this becomes something nice? I want to find a replacement for x. X equals something, so that when I plug that in and square it and take its square root, I'm able to integrate that nicely. And this is where I'm going to look back at my table. These are some of the trig identities that I expect people to be able to know. We all know sine squared plus cosine squared equals 1. When I divide everything by cosine, I get tan squared plus 1 equals secant squared. So a nice candidate, because I have something squared plus a constant, my nice candidate is going to be tangent, and I'm going to choose 3 tangent theta. And the reason why I'm choosing 3 and not 9 is because I'm setting x equal to this. When I square x, I'll get 3 squared, which is 9, times tangent squared, and I'll be able to factor out the 9, that I want the 3 to match the 9. So really it's the square root of that a in front. Or I guess I called it a squared in some of the forms. All right, so now we have our candidate for x. That means that dx, the derivative of tangent is secant squared theta d theta. We go ahead and implement our trig substitution. I'm going to plug in 9 plus x squared is going to be 3 tangent theta all squared, and then dx is going to be 3 secant squared theta d theta. It sort of looks like a u substitution, but really it's backwards because I'm making x a function of something rather than making u a function of x. I can simplify this. That's the whole point. This becomes the square root of 9 plus 9 tangent squared theta times, I'll pull this 3 out front of the integral, secant squared theta d theta. Now let's factor out that 9. From each of these terms, this becomes the square root of 9 times 1 plus tangent theta, tangent squared theta, times secant squared theta d theta. 1 plus tangent squared is secant squared. That's the whole reason why we did the substitution. The square root of 9 is 3. So that becomes 3 times the integral of 3 secant squared times secant squared theta d theta. So notice I made a little error here that this, sorry, the 1 plus tangent squared becomes secant squared, but then when I take the square root of it, it ends up just being secant theta. And that makes a difference for this integration. So this becomes 9 times the integral of secant cubed theta d theta. And this is actually a good exercise in terms of reviewing integrals of trig functions, but I'm not going to take the time now to go through this integral process. Instead, well, maybe you could look it up on a different video as well. I can use an integration table as well to find out that the integral of secant cubed is actually 1/2 tangent theta secant theta plus 1/2 of the natural log of secant theta plus tangent theta plus c. Great. So we did this substitution. We were able to integrate using a table or using trig identities to be able to integrate it. Whoops, I'm missing a there. But we aren't done yet. There's still the hard part. The hard part is converting these back into functions of x. So let's set up the triangle and recall what pieces do we know and what pieces do we not know. The way that we set this problem up, that tangent of theta, I'll write it down here, tangent of theta is equal to x divided by 3, which is the same thing as opposite over adjacent. So in this case, opposite over adjacent, I have x, I have 3, and that means the hypotenuse in this case is x squared plus 3 squared, which is 9. And that's the information that I need to be able to fill in some of the pieces. I'm also going to need to know, we know what tangent theta is, I need to know what secant theta is. Recall that secant theta, cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent, which in this case, well, maybe I should write it out, hypotenuse over adjacent, which is x squared plus 9 over 3. So once I've used this triangle, I can go back to this solution and find out that my solution can be rewritten as 9/2 times, what's the tangent of theta? X over 3 times the secant of theta, which is x squared plus 9 over 3 plus 9/2 times the natural log of the secant of theta, x squared plus 9 over 3, plus the tangent of theta, which is x over 3, plus c. And I can simplify this slightly. Notice that the 9 is divided by 3 times 3, and I can do the distributive property, so my first term ends up being x to the third plus 9x all over 2 plus 9/2 times the natural log of x squared plus x plus 9 all over 3, whoops, ran out of room, plus c. So in my final example, we're going to look at making use of yet one more trig substitution, and notice that this function is sort of embedded within a bigger function, that I can still identify the fact that I can rewrite this integral as the square root of something. In this case, it's the square root of x squared minus 4, something squared minus a constant, all raised to the third power. And so I'm going to isolate this radical and think, what trig identity can I use to be able to make this radical look nicer? I'll bust out this sheet of paper. These are things that I expect you to know. Before, we found, just from sine squared plus cosine squared equals 1, we get tan squared plus 1 equals secant squared. That's not exactly what I want. I want something squared minus the constant. We have that secant squared minus 1 is tangent squared. So I think that I want my x to be a function that looks something like secant. In order to match this coefficient, I'm going to put a 2 out front, because now when I square it, I'll be able to factor out that 4. Let's take a look. If I set this x equals to 2 secant theta as my substitution, I take the derivative dx. And what's the derivative of secant? It's secant theta tangent theta d theta. So I can look at my original integral and perform the substitution. My dx becomes 2 secant theta tangent theta d theta divided by, I'm plugging in 2 secant theta in for x squared. 2 secant theta becomes my x. I need to square that piece and subtract 4. And then this whole thing is raised to the 3/2. We can simplify, and I'm going to simplify a little bit quickly. I realize that there's a lot of writing in these examples. Squaring each of these terms and factoring out the 4, I get 4 times secant squared theta minus 1, all raised to the 3/2. Secant squared minus 1, recall, is tangent squared. And I'm not going to make the same error that I made in the last video. This 4 is also being raised to the 3/2 power, so I'll write that as 4 to the 3/2 times tangent squared theta to the 3/2 is the denominator, and the numerator is 2 secant theta tangent theta d theta. 4 to the 3/2, the square root of 4 is 2, 2 to the 3rd is 8, and it's in the denominator, so it's 1/8. Oh, the 2 I can also pull out front, so I'll make this a 2. Right, I just pulled out these coefficients. The numerator stays the same. The denominator becomes tangent squared, square rooted, so I get tangent to the 3rd. And I can simplify. This becomes 1/4 times the integral of this tangent to the 3rd. Oh, what's the derivative of tangent is secant squared? That's not quite good enough. Maybe I should cancel out. So this becomes secant theta over tangent squared theta d theta. To figure out how to integrate this, instead of looking it up into a table, I haven't quite simplified it down yet. I'm going to, well, maybe we'll skip back up over here. I'm going to convert everything in here into sines and cosines. That just makes it easier for me to see the possibilities. So what is secant? Secant is 1 over cosine, so I'm going to move the cosine into the denominator. And what is 1 over tangent squared? Well, So maybe I'll write this as 1 over cosine. Tangent is sine over cosine, so the reciprocal of that is cosine over sine. And simplifying all of this out, this cosine squared, one of them cancels, so I end up with a cosine theta in the numerator, and I end up with a sine squared theta in the denominator. To solve this, I'm going to need to do a u substitution, but it's a pretty straightforward u substitution. I'm going to let u equal sine of theta, because then du can be equal to cosine of theta d theta, which is exactly what we have in this numerator. So I end up with 1/4 of the integral of 1 over u squared du, which is 1/4. I can integrate this. Hooray! This is u to the negative 2, right? So this becomes u to the negative 1 times negative 1 plus c, or I can rewrite that as negative 1/4 times 1 over u. Well, what was u? U was sine of theta, so this becomes negative 1 over 4 sine of theta. Whoops, and I dropped my plus c. Plus c. Hooray! So we did our substitution so that we were able to integrate. We integrated. Now that we have this, we still have to do one last step. We have to convert our thetas back into x's. And just looking at this, I need to have my picture in order to know how to convert these back again. So I draw a picture. What was my original relationship? My original relationship was, maybe I'll even write it in red to offset it, that the secant of theta is equal to x over 2. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. So looking at this angle theta, I'm going to let my hypotenuse be x and the adjacent side be 2, and that means that by Pythagorean theorem I can solve and find what the length of this side is, which is the hypotenuse squared minus the other side squared, square rooted. And if that's what this triangle looks like, I can use that information to find out what sine needs to be. Sine of theta is opposite over hypotenuse. So in this case, that's going to be the square root of x squared minus 4 divided by the hypotenuse x. Plugging that back into my integral value, I see that my final integral value is negative 1 divided by 4 times the sine of theta, which is the square root of x squared minus 4 divided by x. Or taking the reciprocal of that, I think it's a little nicer to be able to write it as negative x divided by 4 times the square root of x squared minus 4, all plus c. Forgetting my plus c's. And there is a radical in the denominator, but I've already done a lot of work. You don't need to see me clear radicals and denominators. So let's summarize. This is a pretty tricky section, right? There are a lot of procedures that we talked about, and I'm going to talk through what we did. So first, when looking at these integrals, it was always something squared minus an x squared, or plus an x squared, or x squared minus something square rooted. And depending upon those three cases, we have three different options. First, you could have, if it's like 1 minus x squared, then we're going to need to use a sign identity so that our substitution, and maybe I should write in the substitution in this case is the fact that 1 minus sine squared is equal to cosine squared. And then when substituting things back in, you have to draw the triangle and find out what the opposite and the hypotenuse are from this identity. You can figure out the adjacent to find out the other trig elements that you might need. The other substitution we saw was the idea that tangent squared theta plus 1 is equal to secant squared theta. So when I add these together, I could square root it and get a secant. And then when plugging back in, I can use these triangle identities. And then finally over here, we use the fact that secant squared theta minus a constant, or minus 1, is equal to tangent squared theta. And these were the triangle substitutions. One of the tricky parts of this section is the fact that even once you can simplify it into a trig integral, sometimes those trig integrals are really hard and you're going to need a table to evaluate them. And that's one of the reasons why I will provide a table to be able to evaluate some of these tricky substitutions, or tricky integrals.